Hello everyone and welcome to my new lecture. If you remember, 2 weeks ago we have started the discussion on the different applications of motion control, including multi-degrees of freedom systems. But today I'll give a stop on this for 1 week temporarily, and I'll continue with a short review of the introductory material based on the requests coming from some of you. I wasn't actually planning to do so because I already covered these with a lot of details. But some of your friends sent me mail telling that this is their midterm week and they want to concentrate on their midterms, and they still lack in the basic material in the very first of the course. So that's why I wanted to make a review on this material, and from next week on we will continue with our schedule and follow the practice on motion control systems with time delay, and possibly motion control systems with functional constraints and functionally related systems. Let me go back to the very beginning of the course and make a very fast review of what we had at the beginning of the course. So, I'll try to address the same thing, the same content, with a little bit different approach. Let us take a general robotic system, because I know that most of you are having problem to create the links between the robots and the motion control environment. I also want to address that detail here in that lecture. So let's have a look at two examples. I'll try to draw those examples for you. Now, let us assume that we have the first robot as an elbow manipulator. So let's change the direction and take this as your elbow manipulator. Okay, so the tip can move in X and Y, and we have, if you can see, rotary joints, which means rotary motors in that robot. Let me try to be more precise on this. Okay, so that's the first example, and let's have a look at a similar robotic system with different type of actuation. Let us, for example, take a sliding let's take a sliding joint mechanism here for the x-axis and for the y-axis. Let me draw it nicely for all of you. Well, I think this is the best I can draw. I'm not a good guy in drawing. Alright, so we can call this a robotic system with sliding X and Y actuation. So you can basically assume that these sliding mechanisms are linear bearings in the system. So that's also moving in X and Y. But there's a difference here. Maybe I can draw these lines for you and put them with a different color. Let's take for example red here. So this is, I'll call this theta 1, and this is theta 2, and I'll call that length as L1 and that length as L2, and the tip of the robot in both scenarios goes to the same point, same x y point. Okay, let's take this to be the same x y, or let me put x bar y bar to be more specific. So that's a system basically with, so this is a system with rotational or rotary actuation, and this is a system with linear actuation. Both systems are 2 degrees of freedom systems. Okay, so specific names are planar, elbow manipulator for the robot on the left hand side, and that's called a Cartesian manipulator for the robot on the right hand side. So we have two systems. One is actuated with rotary actuation and the other is actuated with linear actuation. Well, let's first keep that in mind. Now, when we're talking about generalized coordinate of motion, we will be basically referring to the same entity, so that's actually Q, which is nothing but the theta for rotational rotary systems, and it's nothing but L for linear systems. Now we have to keep in mind that this Q is the generalized coordinate of motion. What I mean here is that regardless of the structure of the robot in hand, the same Q can be used interchangeably for rotary and linear systems, because we may, without loss of generality, we may have a system with linear and rotary actuation altogether. Let's have a look at such a system. So, example, system with linear and rotary actuation. Let's draw an example of this. Well, let's again play with the planar system, because planar systems are the easiest among the multi degrees of freedom systems. Let's have a groove here where a sliding contact point can move, and around that let us have a structure like this which can rotate. So here, let me go to the previous slide and take the same color here. So here we have 2 degrees of freedom again, The first one is L, and the second one is theta. So, in such a system, we can again go to the same point, x bar, y bar, and we can simply call the axis back as x and y axis. So here, theta and L refer to two different actuation mechanisms. L is a linear actuation, that's the first link, and theta is the secondary link attached on the first link. So its horizontal position is defined by L, and its angle is defined by theta. Please have a look at the structure in detail. You can observe that it can span xy plane again, with of course certain limitations based on the length L here and based on the range of theta angle. But without loss of generality, we can call this as the first generalized coordinate of motion and this as the second generalized coordinate of motion. So I want you to focus on that notion, generalized coordinate of motion. So it can be used for linear and rotary systems all together. And we will all make our derivations as we did at the beginning of the lecture set in the first weeks. We will all make our derivation based on the assumption that this Q can sometimes refer to rotary system or can sometimes refer to the linear systems. Okay, so without looking at the detail of what Q represents, we will be deriving our equations, because no matter if your system is linear or rotary, we will have the same dynamics. So let us start. What title did we put? Okay, that's a fast review. Let me start here. The concept of well, let me say uh, disturbance. Or before the disturbance, let me say here concept of acceleration control. After introducing the basics, uh, actually, before the acceleration control, I have to also review the structure of the motor. If you remember, that linear actuator or this rotary actuator here, both of them are motors basically, right? Either direct drive motor that can move back and forth as a linear motor, or a rotary motor attached to a mechanism that can create linear sliding motion, or the second motor is already a rotary system, either working directly or with a gearbox. So when we're talking about motors, we have to keep in mind that the motors are driven by the drivers, which take power from a power source and direct it to the motor based on the applied reference. And the mode that makes use of this structure is called the torque control mode or current control mode. So basically, we generate the torque assuming that the torque is a linear multiple of the input current, and we give certain input current to the motor from the driver with a reference signal. So after that, we can move to the concept of acceleration control. Why is it useful? Very simple. Now, with acceleration control, one can let's say play with the positions velocities and forces simultaneously. So what do I mean here? If there's an option to control the acceleration in the system, if there is a magic tool, if you remember, a magic box to control the acceleration of the system, then we will have the opportunity to play with the positions, velocities, and forces. And any kind of multi-degrees of freedom system will have the same variable set, positions, velocities, and forces to be controlled in the system. So, how can we achieve acceleration control? Let me also capitalize this. Okay, how can we achieve acceleration control? Well, all of you remember what we did. What we do is to model the system with known and ideal parameters. Second, assume all other effects be part of the disturbance and finally compensate the disturbances. So we will try to model our systems with known parameters, and we'll assume all other effects to be part of the concept of disturbance, and we'll try to compensate the disturbance. A system with disturbance compensation is called a system that's capable of controlling the accelerations, that can receive accelerations. So let's have a look at the mathematics. Newton's second law. I know that this is the headache for you because you're facing with the same law every time in every class almost, but that's really the guiding law or the governing law of the dynamics of anything. So Newton's second law tells us that the sigma torque affecting on a system is equal to the mass of that system times q double dot. So don't forget that this torque is the generalized torque, and this mass is for a multi-degrees of freedom system, a mass matrix, but for a single degrees of freedom system, we can call it the mass of the, simply the mass of the actuator. Well, in sigma tau, what do we have? We have tau input as the control input from us, minus tau friction, minus the forces arising in the system due to gravity, the forces arising in the system due to external loads, and anything tau, I'll call this additional, anything additional that exists in the system. So that's actually sigma tau. That should be equal to mass times the acceleration response of our system. Okay, let's move to a different color and let me one by one write the content of those details. So tau input is for a generic motion control system where you make use of the motors. It is the torque constant kT times I reference minus tau friction. Well, next semester when you take the robotics class, we will cover the details of the friction force. It's actually not only friction force. For a multi-degrees of freedom system, it's called Coriolis centripetal and viscous friction force term. So if we go back to our slide set, for example, think of think of the first system and the second system. If the first system is moving with certain angular velocity omega, while the second system is moving to the other direction with omega 2, let's say. Obviously, because of the rotation here, there will be certain pushing effect of the second link over the first link. So that is the torque acting on the first link due to the motion of the second link. So that part is simply the centripetal, Coriolis, and viscous friction effect. So I'll call this with the term B of Q dot, because it's dependent on position, on the configuration of the system, and on the speed of the system, on velocity, minus gravity. That's one of the most obvious ones. I will call this G. Actually, let me capitalize these and use capital letters. I'll call this G of Q. Why does gravity depend on the configuration of the system? It's not too difficult to see. For example, here, when theta 2 or Q, when theta, that's Q2 angle, is equal to pi over 2, so when your system and the second link is perfectly vertical, there is no load on the horizontal axis of the first system. So there is no force trying to push this system left or right. But when you put it to an angle like this, due to the moment here, it will certainly have certain effect on the first link. Or here it's better to observe. When the first link is perfectly vertical, there is no gravity effect on it. But when the link is at certain angle, due to the mass of that system, there is a reverse acting torque. That's the external torque. That's the unwanted component in the system due to gravity. Minus, I'll call this tau external the same. That's actually any kind of external force acting on my system. And I'll write here minus tau additional. Should be equal to mq double dot. So if you remember, what we were doing was to divide the system into components that are known and that are unknown. So if we expand this one step further, you'll see that the motor's torque constant is usually dependent on the motor's angular position inside the stator, the rotor's angular position inside the stator. And we have discussed this in the class that KT might sometimes show small fluctuations, small variations based on this angle. So we can assume KT to be equal to some nominal part, K nominal, plus some time varying or position based varying component delta K. Similarly, the mass of the robot, M, can be assumed to be the nominal part, can be assumed to be composed of the nominal part plus varying part, delta M. So with this information in hand, one can continue to further model the system with, let's say, a different color. Well, that would be K, this is K nominal times I ref plus delta K times I ref minus B of Q dot minus G of Q minus tau external, let's write it proper as we did in the first line, tau external minus tau additional should all be equal to M nominal times Q double dot plus delta M times Q double dot. Now, once you have this equation from that one, it's not too difficult to decouple that equation into components that are known and unknown. Simply, if I know K nominal, that's tabulated in the data sheets of those motors. And if I know mass nominal, that's a design parameter. If I'm the guy who's designing the motion control system, I have the software, I can calculate the inertia of the system, or I can measure it actually once it's produced. So these are all known variables. That's also known. And all of the other variables here are unknowns. This part and this part. Okay, so if we know only two of those components, and if we don't know the rest, the remaining part of the equation, it's easy to create an observer or create such a structure by simply looking at the input to output relationship and trying to understand the amount of that unknown force acting on the system. So let me go back to the original color. What we had was this Kn Iref. So K nominal times Iref is simply equal to, I will call this plus this as the disturbance torque in the system. That's tau disturbance plus Mn Q double dot. M nominal Q double dot. So what do we have here? We have this. Actually, it's much better to put a minus sign here and create an equation here. That's simply our input KNIRF is what we give as the nominal input to our system minus anything that can be considered part of the disturbance. So isn't this the net torque, net force in the system? Should be equal to the nominal mass of the system times the acceleration. And here I can simply write that the content of tau this is nothing but all of that thing, delta k iref minus b minus g. Let's write here, but of course here we have a minus sign. That's actually, if you put a minus sign here, that should be with a minus sign, and all of the others should be with a plus sign, right? Let me try to see if there is any problem here. No, that will come with a minus and it will become a plus. Okay, this is b of q dot plus g of q plus tau external plus tau additional plus delta m q double dot minus delta k iref. These are sometimes called the acceleration induced disturbance and the current induced disturbance in the system. So once you model the disturbance of the system with this, and once you simplify your equation to that one, it's not too difficult to create an observer. So can we create an observer for tau this? So what I mean by an observer is that observers are structures that are specific to the governing equations and that are used for estimating some internal variables of a system. So there's actually a huge theory behind that, like, you know, how to create a Leeuwenberger observer. That's a huge field under the control systems discussion or control systems field, but we'll not go into the details of that. I'll simply shorten everything here with the note that the answer to this question is simply yes, we can look at input minus output behavior to estimate the disturbance. So, what's input, what's output? Here in that system, this is input and this is output. So if we change the positions of m and q double dot and tau this, we can come up with that system. Kn times I ref minus m nominal times q double dot. So this is the input given to our system, and that's the response of our system. The difference should be equal to 0 if all of the torque that I give to my system is used for accelerating the system. If part of it is used by some other sources, like by some external torque or additional torque or gravity or friction or anything other, then that will be the component of some disturbance acting in the system, existing in the system. So this equation is important here. And so how can we use the disturbance in the feedback loop? Simply, answer is very straightforward. Well, let me write here. Use a low pass filter. We usually call it LPF. Well, the advantage of using low pass filter is simply the signal that you estimate here in real-time operation is the actual signal, but if you directly feed it back, first, this one and this one, those two signals are very noisy because the current signal is very noisy and the acceleration signal, acceleration response of the system is very noisy too. So using two noisy signal might create problem in the feedback loop when you're trying to get it back and give it as input to your system. So filtering will have contribution to lower the level of the noise. That's the first thing. And second one, maybe more important one, is that when you use a low pass filter, you add a little bit of time delay. Not too much, but very small amount of delay that lets your system first understand the amount of disturbance that existed an epsilon amount of time ago and use it in the feedback loop. So you should first let the system understand the disturbance and then use the disturbance of a very small, a fractional time before, so that your system works in a robust manner. That's why for both of those objectives we use a low pass filter. So what we have finally, we get this tau hat disturbance is low pass filtered version of k nominal times I ref of t, of course this was a function of t, minus m nominal times q double dot of t here. So this is how we estimate the disturbances. Well, there's also one more step here. If we simply try to implement the disturbance with a block diagram, and if we try to make full derivation, we should go to we should switch to the Laplace domain. Let's see. The tau hat disturbance. Let's write it here. So I will move tau as t hat disturbance of course this is a function of time, and we have the function of s here as we move to Laplace domain, should be equal to k nominal times I ref of s, we have moved this to Laplace domain, minus m nominal times s square q of s. So this is m nominal q double dot of t in Laplace domain. All of them being multiplied by the low pass filter. So this is g over s plus g. All right. So this is the structure in the Laplace domain, and without loss of generality, we usually drop the s-dependent term in the derivation and come up with a more clear expression. Tau this hat is equal to kn I ref minus mn s squared q of s, or mn s squared, times g over s plus g. Don't forget that this is actual disturbance, that is tau this of s, and when you multiply it by the low pass filter, you basically get tau hat this of s. This is the estimation. An estimation comes with the low pass filter. Here that g is pretty important. Well, I think all of you remember how we created the block diagram, but let me go through those equations and try to further create for you the block diagram. So tau hat this of s is nothing but k nominal times I ref of s times g over s plus g, that's the low pass filter, minus, here we have m nominal times s q of s times, I can write here this as sg over s plus g. Okay, and let's move to a different color. Observe this. Sg over s plus g, that's not physically realizable. So when we say physically realizable, we are referring to applicability of the operation in real system. So any system in Laplace domain that has numerator degree equal to or greater than the denominator degree cannot be physically realizable. That's kind of a philosophical discussion, but what you should understand from there is that there is the derivative exists in that system when you have s in the numerator. So a system where you have the derivative cannot be realized physically, because derivative means that from now you're trying to see the future. That's the inverse operation of integral. Integral is looking at the information collected in the previous time steps. So it's summation of those, but the derivative is looking at the next step and looking at the difference between the next step and this step. So that's not physically realizable. And in order to implement this in real time, we're basically making a switching here in that function, and we're writing this function differently. This is simply 1 minus g over s plus g. So if you look at that, this is s plus g minus g, so that's s over s plus g, right? All multiplied by a g outside. Or you can write it directly as g minus, or actually that's easier. That's easier because this is easier to implement. Have a look at this. This is s plus g minus g. So you simply have s in the numerator, s over s plus g. When you multiply it with g, it's sg over s plus g. and it's the same thing here. So we will basically replace that with this. Let me go to my original color and let's go to the next slide. So we have the tau hat disturbance of S being equal to k nominal times I ref of S times G over S plus G minus, let's go back, that's M and S Q of S. So M nominal S Q of S times, instead of Sg over S plus G, I'm going to write this G times 1 minus, so that's G times 1 minus G over S plus G. So if we want to rearrange this equation, we're going to get this tau hat disturbance of S is equal to k nominal times I ref of S times G over S plus G minus M nominal times G times Q. Well, we can write here simply omega of S. That's S times Q of S, right? So this multiplied with 1, and minus times minus makes a plus. So plus M nominal times G times omega of S times, here we have G over S plus G once more. So the same G over S plus G multiplies this term and this term. So we can simply call tau hat disturbance of S to be equal to k nominal times I ref of S minus M nominal times G omega of S. I'm sorry, this should be plus, not minus. All being multiplied, so this one and this one, all being multiplied by G over S plus G, that's a low pass filter, minus M nominal G omega of S, where I should write here that the omega of S is simply S times Q of S. That's the speed response of our system. Okay. Most of you already know, but I'll try to address the way we put this in a block diagram. So let's write it here, block diagram. Or let me give the block diagram in the next slide. We have more space there. Block diagram. So let's have a look at the system. We have summation point where we simply give our input torque, right? And our input torque is calculated by our input reference, right? Let me try to put here a summation for future and create this. Okay, that is torque constant of the system, IRF times KT. Now, I know that you're worried about this part. I'm gonna draw it later on. So this is tau input, and here you have the, let's make it with a different color. Here you have the disturbance acting on your system. Tau disturbance. By the way, I'm not following any football team, so don't be misled by those, you know, yellow and red colors. I'm not a Galatasaray fan. I'm not a fan of any teams. You know, I'm not following any football team. So, okay, here tau input is here, tau disturbance. We can call this to be acting with a plus and minus sign. So that will be simply divided by 1 over m it's actually multiplied by 1 over m or divided by m to yield to q double dot, right? This is q double dot, and it can be integrated. I can write the integral this way, or with 1 over s, as you have it in MATLAB Simulink environment. 1 over s here again, and here you have q dot q double dot. Okay, so what we do is this q double dot and IRF given to the system can be taken to a control loop. How to do it? Let me actually, it's not this one, not that one. I'm sorry, I'm gonna change it a little bit. I have here IRF, and here the summation point, and this one is I input. Okay, I'm taking a node from the input current of the system, multiplying with K nominal. Let's have a look at the equation. K nominal times IRF of S. Okay, maybe I can call this IRF for you, and let's call this I desired I reference. Okay, so IRF times Kn is here, and it will be added on this, of course, once it's being multiplied with m nominal and g. So we can erase this m nominal, and then there is the constant g here. So we can add these two signals, right? Simply it's IRF times Kn and q dot times m nominal times g. So all of this should go through a low pass filter, g over s plus g, right? And it should be sent through another step where you subtract the same m and g multiplied velocity term. So that is, here you have the g term, here you have the nominal mass m nominal, and simply you take a node here down to this, and this is subtracted. So that signal here is nothing but tau hat disturbance. But since we're giving the desired current to our system, we have to make a final operation and write here that I hat disturbance is equal to 1 over K nominal times the tau hat disturbance. Okay, so we have implemented all of the derived material there, and let me take this. Okay, that structure here is referred as the disturbance observer. Sorry for this. Okay, that's our disturbance observer. All right, let me look at the time. I think I'm a little bit out of time, but I'll try to finalize this slide set with some additional notes. Let me give a break here so that you can have a fresh air before moving on to the next video. And in the next video, I'll make the analysis on the uncompensated disturbance, on the performance of the disturbance observer, and I'll try to make the derivations for three fundamental control structures: velocity control, position control, and generalized error control. And I'll try to show you, or I'll try to restate once more the details on two-loop control system, like the inner loop acceleration control and outer loop task controller. See you in the next video set.